Hello, this is Mr. Craig, and I want to talk about zero order reactions. I've already talked about first and second order reactions from the previous days. I want to talk about temperature and rate, collision theory, and activation energy. Let's first of all start off with zero order reactions or reactant. We've already talked about zero order reactants in that it is a reaction that regardless of what the concentration is, the rate remains the same. So I can double the concentration, the rate remains the same. I can take 1/4 of the concentration and the rate remains the same. So it's a really strange situation. I can't think of too many reactions that do have zero order reactants, but they do exist out there. And so again, the equations are given here, and what's really bizarre is this equation is not on the equation sheet. So what does that say about it appearing on the AP exam? Well, the concept will appear, but there won't be any math on the AP exam. So if you're wanting to find the half-life for a zero order reactant, the equation simply is stated: you take the initial concentration divided by 2, and that's equal to the negative kT plus the original concentration. Probably, in other words, just take the initial concentration divided by twice the rate constant K. You won't be doing any calculations with these, unfortunately. So, sorry about that, guys. At the bottom of the page on the front side here, I have a summary of all the rate laws, the orders, and the type of, especially right here, I don't know if I can highlight this, but this middle row right here probably is the most important thing that you need to know for the concepts when it comes to the AP exam and being able to determine the type of graph and what the order of the reactant is. Also, this next row here where it says the slope is negative K, and then for a second order positive K, that just reinforces this middle row here. So again, take what you want from this. For calculations, we'll only do first and second order type reactants. Alright, on the back side, let's talk about the relationship between temperature and rate. We've already talked earlier, and I can't recall when we did this, and I think it may have been with gases. That actually makes a little more sense. But the relationship between temperature and the rate of a reaction, if the temperature of the reaction increases, generally speaking, if it's not an equilibrium type problem, the rate of the reaction will increase. The reason why is because as we increase the temperature, we're increasing the amount of energy that's present with all the reactants, and they're able to find each other more quickly, collide more easily, and actually form the products. And we'll talk about collision theory here momentarily. But generally speaking, as the temperature increases, so does the rate of reaction. Temperature decreases, so does the rate of reaction. One general rule of thumb that isn't published too often, but I learned this in my organic class. As you increase the temperature of the reaction by 10 degrees Celsius, you typically double the rate. Now, that has its limits, and there, of course, are exceptions to that. But if I double the temperature, if I increase the temperature of a reaction or of the system by 10 degrees, I can get the rate to double or become twice as fast. Also, if I place, say, the reaction in an ice bath to cool it down, if I could cool it down 10 degrees, then I could actually have the rate go twice as long. In other words, it's slower now. So yes, temperature and rate are directly proportional, generally speaking. All right, collision theory. Collision theory talks about being able to collide correctly and form a product. In other words, just because one particle bumps into another particle doesn't necessarily mean that it's forming a product. It's kind of like pieces of a puzzle. The pieces of a puzzle will fit just correctly with the other piece. You can't force, well, you could force, but you don't want to force the two puzzle pieces together if you turn them, say, 90 degrees from each other and try to fit the pieces together. So when we talk about collision theory, it's all about making the right connection. And if this connection is not made, then the product is not formed. So, and again, when you increase the temperature of a reaction, you increase the possibility or the probability that they'll accidentally bump into each other in the correct way. Now again, by having those particles move around more quickly, that increases the chances that they'll collide correctly. All right, activation energy and activated complex, and we'll talk more about this when we do thermodynamics, I think in the next topic or a couple topics from now. But when we talk about activation energy talks about the amount of energy needed for the reactants to change into the products, or the amount of energy that's needed to, quote-unquote, start the reaction. Actually when I say start, I mean to have the reactants form products. So it's like the analogy that I use in classroom. I say, okay, on my desk I've got a big bowl of gasoline. If I take a match and I throw a match on the bowl of gasoline, what will happen? And oftentimes the students will yell, oh, it'll explode, it'll blow up. And then I'll say, no, the match isn't lit. So if I just throw a match on a bowl of gasoline that's not lit, nothing will happen because it doesn't have that enough energy to get the reaction to start. However, if that match is lit and I now throw it on the bowl of gasoline, now we've got a light show. So the amount of energy needed for the reaction to take place means enough energy for the reactants to combine in the correct way to form the product. The graphs here actually show a couple different things. Typically, the two graphs here on the right are pretty typical of what we talk about. And in other words, the reactants start off with a certain amount of energy, and then we need to add enough energy to change those reactants into products. And then on the other side, depending on if it's an endothermic or an exothermic reaction, it'll either be the amount of energy will be lower or greater than the amount of energy that the reactants start with. So we'll talk more extensively about endothermic reactions and exothermic reactions when we talk about thermodynamics. The graph here on the left actually shows or tries to represent which set of conditions or which temperature has more reactants changing into products. And the T's represent temperatures. Now often I'll ask the students, and they'll even see this T2 is greater than T1. I'll ask, which temperature is greatest when we look at this set of data here? And oftentimes the students will look to the left, but they don't realize that this E sub A represents the activation energy. The activation energy is this point right up here, or the amount of energy needed to change the reactants into products. So that's what this is right here. Once we've hit that point or that amount of energy, then the reactants have changed into products. So the blue line, or the T1 here, has a much lower temperature because more of the reactants are still below the activation energy, and there aren't as many that have changed into products. However, T2, more of the reactants are at a higher temperature and they have enough energy to change into products. So the T2 actually is at a much higher temperature than T1. And if you did a volume or an area estimate here, you would find out that the area is the same below each of these graphs respectively. Alright, looks like that's all I want to talk about for that page. I hope this has helped. This is Mr. Craig, and I want to talk about the last page of examples for day 103 in kinetics. Part C is the first thing I want to talk about is reaction mechanisms. Now, up until this point, we have talked about a balanced equation looking very, very simple, like this equation right here. We always start off with a set of reactants, and we finish with a set of products. And based on these reactants and products, we're able to balance the equation and be happy and move on in our happy, joyous life. The reality is, most reactions that take place in the universe do not happen in one quote-unquote step. There's what's called intermediate steps. In other words, what we can't see is what's going on with this arrow. In other words, how these reactants changed into the products here. If we look at this reaction here, the reality is that there's actually two steps in the reaction where two nitrogen monoxides, and this isn't balanced. I don't believe. It may be, it may not be. The balanced equation, the reaction takes two molecules of nitrogen dioxide and forms a nitrogen trioxide and a nitrogen monoxide. And then in the next step, that nitrogen trioxide reacts with the carbon monoxide to form the products nitrogen dioxide and carbon dioxide. Now, when we look at this reaction, we have to recognize that there are things on both sides of the equation that, quote-unquote, don't even appear in the balanced equation up here. Like, for example, the nitrogen trioxide does not appear at all in this balanced equation. We have a total of 3 nitrogen dioxides in the equation, but we only have 1 up here in our original equation. The good news is you will never ever have to predict intermediates or reaction steps. If you go on with chemistry, you'll find out that as a reaction takes place that there are these intermediates that are formed, and sometimes you may want to stop the reaction when a certain intermediate is formed. But for the scope of this class, we aren't going to be concerned about the intermediates, and they will be given to you. So whenever you look at an equation that has quote-unquote elementary steps or steps of the reaction, we want to cancel out alike terms. Now what I've done here in this is I've shown the 2 steps of the reaction. I've written everything down. These are all the things that are on the reactant side, and these are all the products that are on the product side. And then what we want to do is cancel out alike terms to get our final balanced equation. And we'll do an example like that here in a moment. But the key here is you do not have to predict intermediates. And again, intermediates are products that are produced in between the first step and the final step. Okay? So don't freak out on that. You'll always be given that information. Let's do an example problem here. The example says, using the 2 elementary steps shown below, construct the balanced equation to determine, actually there's more than 2 steps here. There's actually 4 steps. So we're going to work out and find out which things can be canceled out and which things move on here. So we're going to get a balanced equation here. So I'm going to move this up just a little bit. Let's go ahead and go to this part. I'm going to draw on here. Whoops, I did not want to do that. Let's cancel that. Let's go back. Okay. So first thing that I want to do is I want to cancel out anything that shows up on opposite sides. Like so, for example, here I have an oxygen here and an oxygen there. That one can go away. So that will not go down here in this balanced equation. I have 2 nitrogen dioxides, but they're on the same side. I do have a nitrogen trioxide here and a nitrogen trioxide there. I also have a NOF on both sides, and I have NOF2 on both sides. Now let's check for the remaining. There are no, oh there is one. There's one NO2 there and there's one NO2 there. Alright, so there's no fluorines, F2s on this side. There's 2 NO2s on this side, but no others on this side. So let's write down everything that remains. So we have 2 NO2s plus a fluorine, which yields, and everything that remains, looks like we have 2 NO2F. Now, if this was done correctly, we should have the same number of atoms on both sides. So let's check where we have 2 nitrogen, 2 nitrogen. We have 2 times 2, which is 4 oxygen, 2 times 2, which is 4 oxygen, 2 fluorine, 2 fluorine. We are good to go. Okay, so these are actually fun problems. What I don't want you to do is freak out and look at the steps and say to yourself, whoa, how are we supposed to do this? Cancel out terms that are on opposite sides of the arrow. I'm not sure what that property is in math, if it's the associative property. I'm not a math teacher, so I'm not 100% sure. But if it appears on opposite sides of the equation, you're going to cancel it out. You're not going to cancel everything out. In other words, like the NO2 that was here, we didn't cancel all the NO2s. We canceled one of each. So it's kind of like doing the redox problems that we did earlier in the year. All right. determining the rate laws from the elementary steps and the rate determining step. Now up here, I didn't tell you which reaction or which step was fast and which one was slow and so on and so forth. I just gave you all the intermediate steps, and I wanted to know what was the balanced equation. Down here in this problem, we can actually determine the rate law from the rate determining step. And the way that we do that is you'll be given information, and if you're asked to do this, you'll be given information where you'll see things that say this step is fast, that one's fast, this one's slow, this one's fast. And we don't really care how fast is, just realize that it's faster than the slowest step. So when we go in, determine the rate determining step, it's kind of like an analogy that I use. When I go into the grocery store, I know exactly what I want to buy. I'd say I need to go pick up a gallon of milk. I have to walk all the way through the store to the back of the grocery store, grab the milk, and then I go to the checkout counter. And before the U-Scan or the self-serve aisles were produced, this was a great story. But I would have to stand in line and wait for all the other people to get checked out, and then when it was my turn, then I would pay for the gallon of milk and then leave the store. Now, there were a couple steps there. First of all, getting into the store, going and getting the milk from the store, going to the line, getting through the line, and then getting out. And the rate determining step for me is always the checkout line. In other words, I have to stop and I have to wait and I have to watch other people use their coupons, write out their checks. Unless I'm doing a 5-finger discount, that is the rate determining step. I cannot get out of that store any more quickly than getting through the checkout aisle. So when we look at a reaction, the slow step is the rate determining step. So if we know what the rate determining step is, then we can actually go and do a real neat calculation here and actually write down what the rate law is based on that. And here's how it goes. The rate law can be determined if you know the rate determining step. The rate law will be written to include all the reactants minus the intermediates up to and including the slow step. So the first thing that we need to do is find the slow step. So what we want to do is we want to eliminate all intermediates. Again, an intermediate is something that is produced and later used as a reactant. So our first intermediate that's produced is C. A plus B yields C. And then C is later used as a reactant later on. So product that is used as a reactant, that is an intermediate. Okay. Now these two B's here are both reactants, so we're not going to cancel any of those out. Plus they're on the same side. Then if I look at the second step where it says C plus D forms D and E, both D and E are intermediates, so they are going to get canceled out. So I don't want to even look at those. Now that I'm to my slow step, I have to say to myself, I'm going to include all reactants minus the intermediates. Well, the only thing that remains up until the slow step is 1A and 2B's. Okay, this is my rate. This is to write my rate law. So when I look at this, I can now write my rate law as this. Rate. Actually, let me lower this down a little bit. Rate is equal to whatever K is. We don't know what K is yet. And since I have 1A, that is a first order reactant. And I have 2B's, that is a second order reactant. So my rate law is right here. So again, I'm going to show all reactants up to and including the slow step minus the intermediates. Now, remember, a reactant can only be 0, first, or second order. You'll notice that there is a second A that appears after the slow step. We would not include that second A in our rate law because it appears after the slow step. So it doesn't matter what the concentration of this A is because it's not going to speed the reaction up any more quickly. So here's my rate law, and we'll get a chance to do some more work on that. All right, the last thing I want to talk about is a catalyst. Now, we've talked about catalysts in general chem. Catalysts do a couple things. The first thing that they do is help organize a reaction. So a catalyst is an organizer. In other words, it actually takes the particle and positions it in such a way that it can collide correctly with another particle. So it actually causes the activation energy to be lower. A catalyst is never consumed in a reaction. Oftentimes, a catalyst can change throughout the reaction, but it always comes back in its original form. So if I started off, say, with 10 grams of magnesium in a reaction, if I don't get 10 grams of magnesium at the end of the reaction, then it was a reactant. So a catalyst is never consumed in a reaction. It acts like an organizer, and it helps lower the activation energy. So when we look at, say, the graph here, that top line is an uncatalyzed reaction because the activation energy is so much greater because there's no catalyst there. However, when we add a catalyst, it does not require as much energy for the reaction to proceed or for the reactants to change into products. So be sure that you know what a catalyst does. Oftentimes a catalyst may appear in an equation, but it always comes back in the same form. So if I look at, say, this equation up here, I might ask you, who is the catalyst? Or can you tell me what the catalyst is? Well, I'm looking at this, and I don't see anything that starts off A, B, or G. Actually, G is an intermediate, so we wouldn't look at that. So A, B doesn't come back in its original form here. So there is no catalyst in this reaction. And you'll get a chance to do that on the homework. I hope this has helped.